Okay. So good morning all. Let's start the class for today with online mode. So it's still actually it's not the introductions on artificial intelligence, but we are more in searching algorithm and also the heuristic. Maybe for today's class I will give you up to the searching algorithm. So as I mentioned, we will have two kind of algorithm where the heuristic one will be a lot of algorithm, but is as you can see here, I put two basic heuristic algorithm. But I will not deliver it today. I will give it those algorithm on the next meeting or on the next class. So now we just focus on two basic searching algorithm, what we call as the breadth first search and also the depth first search, or we can just call them as the BFS and TFS. So let's start with the basic questions. A farmer wants to get his cabbage, goat, and wolf across a river, and he has a boat that only holds two, and he cannot leave the cabbage and goat alone, or the goat and wolf alone. So how many river crossing does he need? So actually it can be different from our logical. We can get the optimal solutions because we are have more complex thinking way. But if we want to use like the AI algorithm, they will have different answers. Why? So that because it depends on how we put the threshold. If the algorithm built based on a threshold case, but if not, then we should have like I mean, if the algorithm uh built based on like dynamic mode, then we may have some kind of fitness function or even like loss function. So I think you may already heard this case actually, but what we want to learn today is how we try to build an algorithm based on this kind of problem. So we need to model the problem. Some of you may doesn't know that actually if we have algorithm, if we have method, it's kind of like a model, but I didn't say that they are totally same because model, method, and algorithm still have different. But what I mean, model, algorithm, method, as a mathematician, you can see it as a function because they will have input and they will produce an output. Just the way how we interpret it and the way how we use it or implement it, it will be different between or among model, algorithm, and method. So now we try to model the problem such that we can have the algorithm. So before we move to the model, we try to have two questions. So how many different state? I mean, state is kind of like the variable if you are in math formula. And then the next question is that how many different actions? That means that after we know the state, then we should give the action. So actually these two problem is also used by the famous machine learning models, what we call as the reinforcement learning. So when you use the reinforcement learning, you will need to define what is the state and what is the actions. So reinforcement learning somehow is also like the searching problem and also the heuristic problem algorithm, but it more automation one, and it's more how to say, yeah, let's say complex one compared to this algorithm that we will learn today. So based on the previous questions, so the state here, we have the farmer, we have the cabbage, we have goat, and we have wolf. We can yeah, make a symbol or notation for those, like farmer will be F, cabbage will be C, goat will be G, and wolf will be W. And the action that we can have, like backward and forward for each state actually. But if we start with the farmer, then we should go with F first, as you can see here. And then we need to define the next actions here, all possible or all combinatories from what we have from the variables. So let's say for the next actions, we can have like six possible movements from FC, from FG, and from FW, who can across the river Bible. So how to find the let's say the optimal actions from the current state. I mean the from the FC, FG, or FW, even from the forward and the backward. So we need to build a search tree. So tree is one of a data structure where if you may know when you learn programming, so you will learn like an array or list, or if you already familiar with Python, then you will have dictionary like data frame and so on. But tree is one of type data structure, and it's like actually the bigger one is graph actually. So uh, in graph and tree, we will have node and we will have age. Sorry, maybe I can say in mathematics first. So graph, we will have vertex and we will have age set. So another term for vertex is a node, and for edges is actually link. So both are quite powerful to express nowadays problem. Even like in certain model like ChatGPT, they also put like graph structure. So to know yeah, the connections between like diverse features from our data, so we can use graph, especially if we talk about the like in bioinformatics, we have DNA sequence, or if we are talking on the chemistry like drug discovery, so it's quite complex if we just use a grid like a neural network have or has. We may not be able to um, represent the molecules or the chemical compound in easy way. So certain researchers on neural network nowadays, they need, or actually back then in even for conventional machine learning, they went to build a manifold from like many chemical compound or even like DNA sequence using the graph data structure or the tree data structure. So what are the difference between tree and graph actually? So as I mentioned at the beginning, graph is more bigger. So tree is subgraph of subset of graph. And what is the difference? In graph, we still can have loop, but tree it doesn't have. So that is what we will call uh, the previous one with tree because the structure is kind of like tree. So maybe I will give like can I make I hope I can write it and we will have a set of edges here. So based on the definition actually V cannot be an empty set. Okay. But E can be an empty set here. So yeah, maybe we will have V1 for a general form of G, Vn like this. And for the edges, we will have E1 until EM. So what is E? EM actually we will have a pair of two nodes. So VI VG. Okay. So this the like simple definition from graph. And we can also use this term for tree, but for tree we cannot have VI um we cannot have the it's hard to draw the definition actually. Let me correct it. So let's say I will just have this structure. So let's say here I have three nodes. If I mention complete graph, then each node will have link or edge like this. Okay. So this is what we call as graph. But for tree, we cannot have this link actually. Maybe I will try to use different color. So I cannot have this one or I cannot have this part actually or yeah others so that we can have like a tree form. So let's say I will just have this kind of form to make uh difference structure between graph and tree. So like this. Okay. So tree will be something like always around this. We will have a root and we will have leaves or we will have uh, parents and we will have children, and so on. So that's the difference between graph and tree. So based on this definition, actually, we can try to represent the problems that we have, and then we define the algorithm. We can construct the algorithm to find the optimal solutions. So from the previous questions, we can have this kind of tree structure. This is not the optimal one, as I mentioned. Different algorithm may have different solution, and it depends on how we put the threshold, and also what do you have in the fitness function. I mean, if you have certain fitness function or loss function, then it will be have different interpretations to have the optimal solutions. So just want to say that the root before now we have four state, like I mean four variables, like we have farmer, cabbage, goat, and wolf. So I put the root will be FCGW here. And then on the next stage, we will have all possible actions by combining. First is the farmer, and next will be C, G, and W here. So it depends on how we, as I mentioned, define the threshold and the fitness function. So we may think that we should halt or stop on these two leaves or branches, but we still continue for the CW, for the FG. Okay. So how we build a searching problem. So the ideally we follow these general steps. So if we talk about algorithm, I do believe that you already know that, but I just want to mention it again so that we can not get confused between model and algorithm. So if model, we will build like a function. It's more abstract, and then the algorithm is try to uh, describe the function from our model so that it looks like more clear. Clearer, and we have a deterministic way to get the output of the function. So here, the general step for the searching algorithm. First, we have defined the state space here. It's if I like teach on calculus or mathematics class, actually I always say to my student that it is important to know the domain. So like every method, every model, or every algorithm, we should know the domain actually. So here, we should know the state space or the environment. Okay, after we declare the state space, then we can try to initialize the state. So this will be the one that we will, how to say, take a look whether it's already optimal or not. And then we need to divide the goal test by given a state, return whether the state is a goal. I mean, whether we already achieve the state that we think it's optimal. And then we put the actions, and we need to define this successor function, as I told you, like the fitness function or the loss function. So we need to define this one, given current state and action, and then return the new state. So we will also have the cost of an action. So the cost of an action still related to the successor function, like the fitness function and the yeah, or loss function actually. So based on this, actually, it's also used on the heuristic algorithm. Uh, Later on our next meeting, we will try to discuss the difference between the searching problem and the heuristic algorithm. Actually, they have the same kind of step on the algorithm. I mean, the general form one, but they have like a big difference or main difference on the, let's say, the detail action or the detail step. And before I go move, so the algorithm, if you already learn algorithm, we should consider about the complexity analysis by means that we need to make sure that it's deterministic by means that it's finite, not infinite. Okay. So if we consider that, then we should go to the goal test where we will stop when we can determine whether the state goal is a goal. However, the searching algorithm and the uh, heuristic algorithm, if we really depend on whether we already get the goal, sometimes it will be not get the result. Why such that? Because somehow we will like stuck on um or difficult to find the criteria that we want. I mean the stopping criteria. So that is why the computer scientists they just put another stopping criteria or conditions by adding the maximum iterations or the maximum looping so that we can make sure that the algorithm is finite, not infinite. Why it can be like that? We just put the fitness function and we have the threshold, and we think that it will be stopped in certain I mean in certain point, let's say. However, as I mentioned, when we try to calculate the fitness function and we got the result, but if it's too small, the value then will never match with the threshold, or otherwise if the value is always greater than the threshold, when the criteria we just want to the smallest one, then we will never get the result. So that is why the simple idea is by adding stopping criteria or conditions with the maximum epoch or the iterations. You will be fine in any searching algorithm, especially for the heuristic one. We will put like stopping criteria, like maximum iteration. So before I go further, any questions from here? I forgot to tell you, if you have any questions, you can just unmute because maybe I cannot see my screen to check you are a raised hand or something. Okay, I think there is no questions, so I will move. Mm, so here the example of Pac-Man actually. We did some searching algorithm or heuristic algorithm as the agent or as the boot, so that you can maybe you also know sometimes in the game we have like beginner level, medium level, and expert level, or difficult level or hard level, let's say. So it's based on how we if it's traditional one, not like nowadays game. So we just put or define the thresholds. Let's say it's just like a basic logic. So if we want to put like uh s- easy or beginner level, we just put like very small threshold. Meanwhile, if we want to put like hard level, then we put or set the threshold high, so that the player is not easy to, yeah, be the boot or the agent. So here we try to give the, why cannot? Yeah, so the problem is we need to eat all dots here. So the state here, x, x, y. So it's not like Pac-Man is the, actually it's Pac-Man, the state, but now we play on like an image. So image has a pixel, right? In a pixel, we have pixel coordinate. I know that pixel somehow kind of like intensity, but in here we just focus on the position, right? So we focus on the pixel coordinate. And we also have the state is the dot booleans, by means that 1 and 0, whether we have the dots or not. And then we have the action is N, S, E, and W, means that north, south, east, and west. And then successor here, update locations, and possibly a dot boolean. Which dot that we will hit. And then the goal test here, dots all false, because booleans are here like true and false. True means that still have a dots, and false mean that we already hit all. And then we try to go to some destinations. Okay, so the state here like the x and y locations, like the pixel coordinate actually, and then the action still same, and then we have the successor here, update location only. It's nothing about the possible dot boolean, because we just want to make the movement. And then the goal test here, x and y is equal to the n. So for Pac-Man, we already know where is the starting point and where is the destination. So the termination, it's easy to define just by putting the position of the Pac-Man is equal to the end point or the destination point. And also we have same game like Slake, and in 1961 we have the symbolic integrator, where let's say integral x up to the power 4 divided by 1 minus x square to the power 5 uh, divided by 2, and then we have 1/3 tangent cube arc sine inverse x, actually minus tangent sine inverse x plus sine inverse x. So here you can see the flow chart will be something like here, with a substitution where x is equal to sine y, and then we have this and so on. So here the state will be symbolic expression, and the action will be common techniques, and the successor will be the new expression after applying the technique. And the goal tests whether the expression is in standard form or not. We already have the solutions or not. So the common technique example, like integral c f x equal to c integral f x dx. And we also have integral f tangent x dx equal to integral f v over 1 plus y squared dy. If seeing 1 minus x squared, then substitute x with sine y. And we also have an example in a machine translation. So we try to translate from Mandarin to English. So states here current word sequence, and the action will be the next word because it's machine translation. And the successor here, the concatenation of current sequence and next word. So the goal tests whether the current sequence means the same as the current sequence on the English means the same as the Chinese character that we translated, that we want to translate it. So it's another example like when we have questions, then we will have like why, what, how, and then we should think about single and plural. So we will have like why is, why are, and why is, sorry, what is and what are, and so on. And then we go through with the subject. Okay, so this one is kind of like trying to predict the next word from a questions. And the topics here, how we can define which path that we should consider as the optimal solution. So even like this one, it's not all we consider as the solution. It's just what we call as the candidate one. And we can find the optimal solution by tracing and searching it. Let's say we just focus on the why question here, and then we just think about why is, and then we go with is you, is I, are you, and are I. So why are just stop here. Means that it's the optimal solution, but for this it still continue. Okay. So how to find those, how to find the optimal solution or the solution that we want? We can use the searching algorithm and also the heuristic one. For the searching algorithm, we have BFS and DFS, as I mentioned, breadth first search and depth first search at the beginning of this class. And we also have UCS, the Dijkstra algorithm is quite famous to find the shortest path problem, like on the traveling salesman problem. But yeah, nowadays we have a bunch of algorithm to beat Dijkstra one. But I certainly still can find some people still follow or adopt the idea of Dijkstra algorithm. So difference with the DSA2, the state space is exponentially large and it's unlikely well stored the whole state space in memory. So before I go to the searching algorithm, I still want to give you the general framework when we play on the tree structure or the searching tree structure. So we have the state space here and we have the search tree. So as I mentioned to you at the beginning, not very beginning, but yeah, I do believe when we learn the tree structure, I already give you graph. So here we have the state space graph, as you can see here. But then we transform it into the search tree as the solutions. So when we try to define the initial problem or the problem itself, Somehow we have graph structure, but when we try to find the solutions, we will have tree structure in here. So it's kind of like dimensionality reductions. I may say something like that because we have smallest degree from what we have, I mean, reduce the complexity. And here, each node in the search tree is an entire path in the state space graph, actually. And we construct both on demand and we construct as little as possible. That is why I say it's kind of like dimensionality reduction because we try to reduce the complexity from the state space graph to the search tree. And here are the algorithm. We have like a list, an empty list, let's say, expanded. And then we have frontier, the initial stage, and we will have the looping mechanism. So the iteration start from here while frontier is not empty, and we need to choose a node S from frontier. For all action A, S prime will be filled with successor state from state A and action, certain state and action. If S prime has not been reached, put S prime in frontier, and then we move S to the expanded, so we will have a leaf or branch. Nodes are divided into three groups by in here in the algorithm. We have expanded, we have frontier, and we have unreached. That means that expanded, then we have maybe I will just can give you another so here what we call as the frontier, and then here what we call as the expanded, and here the one who didn't extend it will be the unreached. Cannot. So all nodes that are not expanded or frontier. That's the unreached. So place state. So now we try to give you some basic intuition how we search it through the state of graph. So we put the initial state in frontier. We can say as the root, we can say as the parent, but if it's really initial one, we can say it as a root. So here we can say as the root, and then we try to search between this node or even this node. So there are three possible neighbor here. Sorry, there are three possible nodes because we need to check the neighborhood of this root node. And then, as I mentioned, this is the all three possible nodes because it's the neighborhood. And then we consider it as the expanded, move S to the expanded one, and choose a node S from the frontier. So now the frontier will be these three nodes. So we kind of check, let's say now the frontier is this node first. So now we check the possible node. Now we have this node and this node. So then move all unreached successor of S to frontier, okay? And then move S to expanded again because we think that we should take it as the frontier before. And then oh yeah, we still have this node. Oh really? I didn't see before, sorry then. So we have three possible nodes then, not two. I just noticed from here. And now we think that here are the frontier. And then move all unreached successor to S to frontier. And now we will have this possible node and this. So now here we only have two nodes. And we continue. Sorry. Choose a node from S from frontier, and then move all unreached successors of S to frontier. So now we have here, and then here, and this one will be the end of the tree. So if you see what I just explained now, if you follow what I explained now, actually it's quite hard to remember where is the position. So that is why we need to unfold it into three actually, so that you know where is the parent and you know where is the child or the children. So here is the implementation. So we have uh, like pseudocode, let's say, but both are actually can be pseudocode actually. So we will have pop. If you are already learned the algorithm, you will know like this stack, and the termination when goal is encountered. Hmm. So it's like if we talk about stack, then at the beginning we have put S prime in frontier, and then for the next level or next section, we should push S prime to frontier. So if S is a goal state for the terminations, we terminate by using break, let's say. And for here, we put it on the termination on this part. If S prime is a goal state, then we terminate it. So for this is late goal test, and for this one, for the early goal test. It's depend how you put it, the termination again. And as I mentioned at the beginning, if you put like for me, it's kind of like an abstract termination, because we should really get S is a goal state. But somehow in real world problem, it's really hard to do that. It's based on, let's say, maybe it's like vanishing value or like blasted value. We don't know. That I just mentioned at the beginning. So somehow instead of we are using like that, or the while frontier is not empty, we put like another termination conditions by having the maximum iterations. But this is just pseudocode, so we just can write it down, the idea or the abstract form or the general steps from to your algorithm. So actually, if you are reading a lot in academic papers, they put the pseudocode on their algorithm, but it's like really abstract. They will not give you like very detailed like in the coding. So here early goal test allows quicker termination when a goal is found. This is what we call as the breadth first search and depth first search. However, when action are associated with cost and we want to find a minimum cost solutions, cost sensitive, we may have to use the let goal test. It's also what we call as the uniform cost search or Dijkstra algorithm, or the late goal is also an idea that heuristic algorithm will follow. Okay, because the heuristic algorithm will use cost sensitive function. So now we talk about the early goal test, like the breadth first search and also the depth first search. what we call as the uninformed search, because we don't have any informations like the cost sensitive one. We just go through the ideally that we go through the action to the action that we think it's ideal for our solution. So here are the concept of the difference between depth first search and the breadth first search. As the name, like depth first search, so we go deeper and then we go to the next level or site. But for the breadth first search, we go to the side first, the right first, and then we go to the deeper. Okay, so that's the difference between depth first search and breadth first search. But as long as my experience, um, and also the complexity analysis I will show you later on, the depth first search will be the efficient one, but I don't want to say like strongly in this case, because it depends on the problem itself and the viewpoint from the solution. Maybe at certain really rare case, the breadth first search can be fast. I do believe that I can find that back then, but I forgot. Sorry, I didn't put here. So here what we have on the general framework that we just discussed. We will have different thing. So we will pop the news node as from the frontier. So from the previous state graph, so we try to make it tree. So as previously we have SDPE on the tree structure. And if you still remember, we go here, right? After that. So we will have, no, we go through D and we will have BCE. So that is why we have BCE here. E, we also have H and R. And then P, it's only Q here. And then we go through. If it's like the depth first, so we go depth first and then we go to the side. So that means that we should go to S and then we should go to D first, like DEP, but we will go to D first actually, because we want to go deeper one. And then we go to B. So actually when you work with the depth first search, we focus on the left part first, go deeper. Okay. So after D we go to B and then we find A is nothing else. Then we are not going to E, but we going to still on D part because we want to finish the depth the depth one, right? So we go to C and then we check that it's only like A. Then we go to E and then sorry. Oh, here, yeah, E, and then we go to H, and then we go to, yeah, key doesn't have that. Then we have R, and then we have F, and then we have, yeah. So that means that we are not going here, because we think that it's not the solution one, so we just skip it. But actually, if we think that it's our candidate solution, then we go E instead of here, okay? So for this part, we just think that E is not our solution, it's not our candidate solution, we just pass it. So we go to the another side. For the breadth search, so pop the oldest node as from frontier. So actually all still the same here. And for the breadth search, we just go through the site. So here as still the same that we should check. And then we go to D and then we go to E, and then we go to P, and we should check whether the solution, where is the solution? Here is the B and C, H and R and Q. E is not our candidate solution, so we just keep it. So from here, we should check again, still focus on left part first. So we go to the B, and then we go to C, and then we go to H, and then we go to R, and then we go to Q. And as you can see, the candidate solution only A and F. So the other nodes are not the candidate solution. So in that case, we go to A and we go to F. And we still have another candidate solution G. So in this part, yeah, we still go to G. Okay. So that's the difference between the depth first search and the breadth first search, the way how we search or move. Before I go to the next slide, do you have any questions? Okay. Hold a second. I need to... Okay. So here again, now we talk how the difference between the versus and versus. In what cases is the DFS quicker to find the goal, and in what cases is the BFS quicker to find the goal? So does the DFS or BFS find the goal with the smallest depth? So here, suppose there exists a goal at layer less than or equal to D. So what is the time complexity for DFS or BFS to find a goal? So here from BSF, the big O, I do hope that you still remember your algorithm class. B plus B square until B D to the power D minus 1. So the big O will be B to the power D. Okay, so from here, expand layer 1 and then expand layer 2 and so on. So B is the branching factor, M is the maximum depth, goes at various temperatures. So let's say D is the depth here. And the depth for the DFS, the big O is only B to the power M. So now, which one is the most costly? Because they are almost the same, B to the power something, so we need to make sure which one is the biggest one. I mean the larger one between the D and the M. So here, what's the maximum possible size of frontier in the DFS or the BFS? So as you can see, let's say we have the tree something like this. If the case of if M is greater than D, then yeah, this one is the now the sorry the complexity for the BFS still B to the power D, but for the DFS the size of frontier now is B times M. So if the M is greater than D, the time complexity for that versus is B to the power M. and the BFS is the B to the power D. So in this case, DFS will be the longer one, the costly one, but for this frontier size, it can be like the B times M, means that it's smaller one compared to the PFS. If the M greater than D. So DFS can be more memory efficient than BFS? Yes, according to the frontier size, but not with our current implementations. Okay, so here depends on the goal state. Okay, because we omit the check, the algorithm may end up search in same subtrees multiple times. A memory efficient version of DFS for acyclic graph, sorry. So from the previous DFS example, we have something like this. And if S is not an ancestor of S, then a memory efficient version of DFS for cyclic graph. Yeah, this one another example for the memory efficient on the DFS. We handling cycles. And then we go here. Yeah. So we just stop here. Then we check the SRACD. So for the cyclic one, the I think a cyclic one. SACD. Oh yeah, so this one B. So from here, SACE, SICF. And then we have SICFD until SICFG. So now we have update from the DFS. We have M times B to the power M, and space complexity we have B times M squared. And for the breadth for search is the same. For the efficiency, the depth first search we have this one. So the big O will be D times B to the power D, and the space one B to the power sorry, B times D squared. I will not give you this, I think. So can I? Oh, I cannot. That's all. So let's take a look on these two videos. Which one you think that the depth first search and the breadth first search? So this one is the video one, and this one is the second video. Okay. And now we go to the next video. Okay. So which one is the depth first search, guys? A, one or two?
Two.
Yeah, two. Any other? Yeah, it's not okay. I cannot see your answer. How? Let's find a way. Okay, I want you to put the raise hand. Okay. When I say video one is that for search, can you raise hand? I want to know whether you're still active or not here. So video one is the first search or not? If you think that yes, then you can raise hand. Okay, there is no okay. Dea is the first one to say video one is the first search. Any other? Raigan 2. Okay. Okay, now you can turn off the Ryzen. Oh, another one. So now we go to the video 2. Who is think that it's a depth first search on the video 2? Okay. Just want to check whether you are still here or not, and also you understand or not. Still a lot of student didn't raise hand. Are they sleeping? Okay. So let's take a look again. Video one is something like this. Okay. And this one are something like this. Hold a second. I need to check again. Okay. So in this case, actually the depth first search on the second video. Because as you can see here, he tried to put all the actions. It's like we focus not on the depth, but on the side. Meanwhile, the second video, as you can see, it's focused on certain action by means that we go through the depth instead of we go to the side. Okay, so that's the difference between the depth first search and the breadth first search. I think that's all for today, guys. Do you have any questions? I will stop here for Dijkstra. We continue again on the next meeting, and also for the informed search by means that the heuristic one, like the A star and so on. Any questions? Yeah, congratulations for the one who choose the second video, actually. Okay, if there is no questions, I want to discuss about the makeup class. We have two classes, two meetings that I missed. Can we have on Friday morning, like let's say at 8 a.m.? But not this week, not on this week. I mean, after what I want is that we still on the class. Face to face, I mean, because it's hard to find the online one for me now because a lot of classes they're already on the weekend and night. Okay, so can you tell me who cannot on Friday morning? Just two meetings. So all can do that?
Izin Pak, saya nggak bisa Pak.
Kenapa?
Ada kelas analisis 2
Hmm, sampai
jam 9.
oh sampai jam 9.
Iya,
Okay, so how about 9 a.m. then? Yang jam 9 ada kelas juga.
maaf Pak, maksudnya saya mulainya jam 9.
Oh, okay.
Iya,
So we still on 8. Ya nanti kamu bisa keluar setelah jam 9 gitu.
siap Pak.
So how about others? think nine. I think at 8 is okay, sir. Okay. So we start. Where is the calendar? This Friday is still holiday, and this one still holiday. I think we start on 3rd April and 10 April for the makeup class. How about others? So for Matthew, you can do it because it's on the in the morning. Do you have problem? One second for us. Oh, okay. For the classroom, I will inform you later, guys, on WhatsApp group. I need to check to the management first which class is empty for, I mean, which class is available for Friday morning at 8. So we already agreed for the makeup class, and I think I already give you the material for today. So that's all for me. Thank you very much, guys. And before I dismiss the class, I just want to say happy 8th day. Happy for you guys to meet with your big family. Enjoy the trip. If you are still on the road, so I do hope that you put your safety first. And yeah, I need to say in Bahasa Matthew because it's not like common culture in outside Indonesia. So jadi saya ucapkan mohon maaf lahir dan batin ya, Kak. Apabila ada kesalahan dan dari saya seperti ucapan dan perbuatan saya mohon maaf sebelumnya karena ini Kak pertemuan terakhir sebelum Hari Raya Idul Fitri. So that's all for today, guys. Once again, thank you very much. And see you on here. We still holiday here. So we will meet again on 31st March. Okay. See you
Yes, sir.
guys. I will end this Zoom meeting.
Thank you,
You.
sir.
Thank you, sir.
Thank you, sir.
And